Okay, Engineer Osborne here for our second video regarding extinguishing agents, where we're going to look more specifically at the effective usage of water. As we said before, H2O is probably the most common, and I keep saying probably, I shouldn't say probably, is the most common way we're going to deal with unwanted fires. So let's jump right in, not waste any time. And you saw this slide in the previous video. Hopefully you watched that. But how do we put out fire using water? Well, we're reducing the temperature and we're removing the heat. Using a fog nozzle, there are ways where we're also kind of pushing the oxygen away. But it really, when we're talking about water, what we're doing is we're reducing that temperature because of that ability of water to absorb heat. So again, this was a slide in the previous video, but water is cheap and it is plentiful. We have it all around us. In the urban areas, we've got fire hydrants every 600 feet or whatever is the requirement of that authority having jurisdiction. You know, even when we have wildland fires, we're going to get water there somehow, whether it's through water tenders or shuttling water from other fire engines. We're going to use water as much as we can. In wildland, though, there's not as readily available. So what does water do? It cools the fuel below the ignition temperature. And 1 gallon of water will absorb 1,251 BTUs going from the ambient temperature, if it was like 62 degrees, and as it absorbs the heat, it'll go up to 212 degrees and will be steaming, but will absorb that much of the heat in those fuels. Conceptually, 1 gallon of water can absorb up to 9,330 BTUs of heat. That's pretty impressive. So that's why we use it. However, there are times where we should not use water. And I mentioned this in the previous video, but B, C, D, or K, we want to... Now, water is going to be used along with the foam concentrate with Class B, but it's not the water, and though it does bring a cooling effect, actually it's the foam in a more drier, denser condition. It's going to smother the fire. So, with hydrocarbons or flammable liquids, energized electricity, grease fires, whether they're B or K, in fact, in that situation, when that impulse is there, you've got a little grease fire going in your kitchen at home, and you just want to grab a glass of water and throw it in there. And it's the worst thing that you could do. It will spread the fire. It'll have an explosive kind of reaction to it and will make the fire worse. All of our flammable metals, dusts, and shavings, water is not the way to deal with it, though when they get really big, we use copious amounts of water that we pour onto those flammable metal fires. There's a great video from LA City when they had one of those fires. Maybe I'll put it in with our set of videos for this chapter. Okay? But it really reacts explosively. There is another con to water that a lot of times people don't realize. It's not only should we not use it in B, C, D, or K, but water does have a high surface tension or a high viscosity. So our denser fuels, it's going to run off of them. Fires like dumpster fires, compost, hay, cotton bales, all of these kind of things, it's tough for the water to get deep into where the seat of the fire or the heat of the fire is, because it runs off. take a drop of water and put it on your clothes. And it doesn't always immediately absorb into your clothes. It kind of runs off. That's because of its viscosity, its surface tension. So it has that inability to penetrate to the seat of the heat, the seat of the heat. And when that happens, we might leave thinking we've put out the fire, and we get a rekindle. And rekindles are embarrassing. And I know, because I've been at some fires where we got a rekindle, and it's not something you want to do. So in a rekindle, the material was not cooled sufficiently into the deeper sections of the fire. So, let's, talk a little more about it. Water absorbs more heat than all matter, except mercury. It expands and contracts. And it's that latent heat of vaporization is, as the water, that's what we call this process, the amount of heat that is absorbed, and then it turns into steam, or at least, becomes hotter, but most of the time it's going to turn into steam, and it's going to displace some of the fire gases, and it's going to reduce the oxygen in the room, but mostly what it's doing is absorbing heat. Well, how are we going to use water? Well, we're going to apply it in many different ways. And one of the especially old traditional ways, but still is used quite often, is with straight stream, or they call them straight bore tips or straight stream tips. And we have an example in our picture here of various versions. You can use them with hand lines, pump at a pressure of 50 psi, and depending on the size of the orifice, the hole, determines the amount of gallons. Usually these are used with our larger lines. A 2.5-inch line with a straight bore tip can give as much as 250 gallons per minute, depending again on the size of the orifice. So it applies using a smooth bore nozzle. You can have a straight stream with an adjustable fog nozzle at the straight setting. So further to the right usually is the straighter setting, and to the left is more of a fog setting. But it's not as, you get a cleaner stream. If what you really want is a straight stream, you get a cleaner stream with a straight bore tip. But most fire departments, especially on their smaller hand lines, a 2.5-inch line is hard to handle. And when you're pumping those larger amount of gallons, you get a lot of reaction. And even at 50 psi, it's a lot. Whereas with the fog nozzle, we're going to usually go at 100 psi. It has a lot to do with that nozzle reaction. When you have a 2.5-inch line, usually it's two people, two firefighters working together, one backing up the other. There are ways where you can sit on it, or you can kind of use a hose strap or wrap your leg around it, you want to be careful with that. But to try and you lean into it so that that nozzle reaction isn't kicking you on your butt, and then you have a nozzle flying all over the place. It's not pretty. So you usually, with your 1.5 inch, 1 3/4, or inch lines, are going to be using some kind of a fog nozzle. The straight stream absorbs heat by converting the water to steam. The straight stream can be used for reaching longer distances. So the fire is further away, we want to squirt it. And when we have like a master stream, or LA City calls these wagon battery, any kind of larger 500 to 1,000 gallons per minute we can shoot out of these guys. You can get a smaller one, like 200 or even less. But these are usually used for larger gallonage with straight streams. You can really shoot it far. and these are usually pumped at 80 psi. A straight stream used to dig deeper into piled materials too, where you can kind of, I used to call it, you hydraulic it. You're stirring it up and you're pushing stuff out of the way and getting that water deeper into the seat of the fire. Master streams can deliver up to 1,000 gallons, like I said. The other kind of nozzle that's probably the most common when we're using our hand lines is a fog tip of some kind. They're a pistol grip, like you see here, and then there's just a regular D-handle type of grip. They were developed by the U.S. Navy, and with the smaller droplets, you can convert it to steam easier, and you can create a thermal imbalance. However, a lot of research has been done lately that says that when we're turning it, when we use a fog nozzle and just spray it all around the room, and like in this picture here, we've brought it down in temperature, the overall heat of the room, but actually at the lower levels, we've increased the temperature because now the steam is filling the whole room at its temperature, but you're bringing the thermal layer lower, losing visibility, and less visibility. It already probably had bad visibility with the smoke. A lot of research has been done recently, and a lot of the training is showing that it's better to use a straight stream and shoot it on the ceiling, and like in a figure 8, and in little bits at a time, and you bring that thermal layer down in its temperature and prevent from flashover. So you can see that in videos where they demonstrate and show that, especially in some of the fuel training containers where they will set up flashover containers, and you can go in there and use thermal imaging, and you can see that with a straight stream you can hit it on the ceiling and boom, it brings down the temperature. Now you still have decent visibility. You've got a cooler environment where you can move forward and get that water on the seat of the fire instead of steaming up the whole room. It's different fire departments have different policies on that, but that's what the latest research shows. Another way that we can apply water is through water mist. And now water mist is very effective in fire protection systems, especially like with electrical transformers and things of that nature. And what it is it's high pressure, minuscule droplets. And they have to be very minuscule to be considered mist instead of drops. It was used in marine applications where they readily had water outside the ship in the ocean, and they would run it through this system, and by using mist instead of a sprinkler system, which is droplets, they were doing less damage to the equipment. It has to be very fine, and it converts to steam, and it reduces the water damage, and it can create a thermal imbalance and bring the fire under control. It's effective as a fire protection system, but many attempts have been seen where they're trying to make it more available in a firefighting application where firefighters just stick a mist nozzle into the room and fire it off. But it's not proven to be very effective and practical and requires special equipment, special nozzles. So I haven't seen it becoming common use yet for firefighting, but in fire protection systems, yes, more common there. So there are also additives that are used to improve water applications. Wet water is an additive that can decrease the surface tension and make the water more effective in going to the seat of the fire. We also have a thing called slippery water, especially when we're having to pump long distances, that's going to reduce the friction loss and the back pressure. And then there's viscous water that actually makes it even more viscous, more heavy. And there are applications for those, but I'm going to tell you, after just short of 25 years of firefighting and people I've talked to, these things are barely ever used. And they're expensive. But what is used is Class A foam. So why not just use Class A foam? Because it decreases the surface tension and decreases a little bit the friction loss, but not significantly, as far as I know. When we're talking about using water with foams, there are Class A foams and there are Class B foams. You use Class A foam on wood, paper, and textiles. You use Class B foam on flammable liquids. Don't interchange them. Class A is for Class A, Class B is for Class B. Now, whether you're using Class A or Class B, if you use water, the way you get the foam is you add water to foam concentrate, or actually you add the foam concentrate to the water, and that gives you a foam solution. So it's actually just a milky looking water. With Class A fires, will use the foam solution for wildland and structure fires, and it makes it a third more effective on those fires. It makes your water go further. If you have a full, let's say you have a 600-gallon tank, well, by adding the Class A foam, even in a foam solution type of adding, you're going to get like 800 gallons of water. It makes it a third more effective. But if you want foam, which in Class B you do want foam, you have to add air. So we're going to do that either through a nozzle or through a compressed air system. We call that CAF. So foam solution plus air equals foam. In Class A, we will use foam solution. In Class B, we're going to add the air with special nozzles using a Venturi effect or CAF. The consistency of that foam now is going to depend on the ratio of foam concentrate to water to the amount of air. So in our Class A applications, almost every engine in the U.S. now has Class A foam injection system. And if you just use a regular nozzle, it's going to come out as foam solution. And some nozzles actually give a little bit of an aeration, and we'll talk about that in a second. You'll get like a low density foam. It's just very milky looking foam solution, kind of getting foamy. But to really get this kind of a foam where it's going to stick, you need CAF. Or you can use special nozzles for entraining air in, and you can get pretty close to that. You get more like this here. See how it's very runny, and this is sticky. So this is more like a medium expansion foam. Again, to get high expansion, you have to have CAF. With Class B, you're going to have to use an eductor. There are some engines out there that are made for flammable liquids fires, and they can mix it without having to have a separate eductor outside the engine. But most of the time, it's going to be using an eductor and a special nozzle to aerate that, or a CAF. Now, with Class B, we don't want to spray it right onto the product like they're doing here. You want to rain it, roll it, or bank it. You don't spray it straight into the flammable liquid because it will disturb the foam blanket that you're creating. You don't want to disturb that in any way because the heat is still there, and as soon as that blanket is broken, it will reignite. And then we also have special foams like wet chems with Class K. The wet chem comes out, it mixes with the media, that oil media, and it saponifies and creates a foam blanket. Okay, just a couple more slides here. So how do we use CAF? Well, CAF actually, like the word implies, you have to have a compressor. So CAF systems can be added to an engine, or they can be mounted on a separate trailer, but it uses a compressor to inject air into the foam, and that's when you can get, and look at how highly dense this foam is. You get a higher density foam with CAF. There are fire protection systems that use compressors to do this for like airplane hangars and places where they have flammable liquids. But out in the field, they put compressors on engines, and you can get that high expansion foam with CAF. Now, we can use nozzles to get low to medium expansion foam. And the nozzle has little holes, and using the Venturi effect, it adds air into the solution, and we can get some pretty thick foam, but not like the shaving cream kind of foam that can come out of CAF. There are advantages and disadvantages to each one, and I have another video that is just about foam that you can watch where it goes into greater detail. If you are taking this or watching this video in my fire behavior class or in a wildland fire class, you will be doing a project about Class A foam, and you'll go into greater detail in the research materials of what's the advantage of using foam solution, low expansion, medium expansion, or high expansion. High expansion has a slow drain time and can be left on the fire in an overhaul state, and it's great. It just slowly works its way down. Foam solution is going to go deeper right away. So in firefighting operations, we rarely want to use CAF. We want to use foam solution or low expansion because it gets to the heat of the seat of the heat faster. Okay, last one. Application of Class A foams. What I was just saying, that wet foam is usually we're going to use a nozzle of some kind, and it has fast drain time. So foam solution or wet foam when we are, depending on the fuels, when we're fighting Class A fires. Fluid foam, a low to medium expansion, is achieved through using one of those nozzles. Now, we had one of these on my fire engine, and a lot of times we had a car fire that kind of seemed a little stubborn and going out. If we had adequate water, hey, I'm going to have to go fill up anyways before we go back to the fire station. If we had adequate water, I'd ask the guys to switch from their fog nozzle to one of these bigger eductor type nozzles that are going to inject air in, not like a CAF inject, but entrain air in, I should say. And we just kind of use that medium expansion and fill up the engine compartment, the trunk, and the passenger compartment, and just fill it up with fluid foam. And it would, over time, just continue to cool that thing down and penetrate slowly into the deeper parts of the fuels. Now, dry foam, like I said before, attacks all three sides of the fire triangle. It smothers it, it cools it, and it can be used to separate fuels, like in the picture where you saw them putting it on the building to try and keep the heat from getting onto those fuels. The advantage, other advantage to dry foam, other than separating the fuels or being used with a control line on a wildland fire, is it does have slower drain times, so you can again use it where in an overhaul point where you put it on the fuels, and it's just going to over time continue to penetrate into the fuels. Okay, that's it on this one. Almost 25 minutes, but we had a lot of ground to cover.